Hello 10th class students. As many of you will be opting for MPC group or a BPC group in near future, and many of you will be writing the different competitive exams. So here I am going to extend the topic of periodic classification of elements to the next level. So these videos are related to that part. Okay, they are again related to concepts only, based on the concepts, just a little bit of extension of the topics which you have to go through once. Okay, so go through these videos very carefully, try to understand the maximum concepts which are available in this particular videos. Thank you.
Let's think a little bit about the notion of atomic size or atomic radius in this video. And at first thought, you might think, well, this might be a fairly straightforward thing. If I'm trying to calculate the radius of some type of circular object, I'm just thinking about, well, what's the distance between the center of that circular object and the edge of it? So the length of this line right over here, that would be the radius. And so a lot of people, when they conceptualize an atom, they imagine a positive nucleus with the protons in the center right over here, and then they imagine the electrons on these fixed orbits around that nucleus. So they might imagine some electrons in this orbit right over here, just kind of orbiting around, and then there might be a few more on this orbit out here, orbiting around out here. And you might say, okay, well, that's easy to figure out the atomic radius. I just figure out the distance between the nucleus and the outermost electron, and we could call that the radius. And that would work, except for the fact that this is not the right way to conceptualize how electrons, or how they move, or how they are distributed around a nucleus. Electrons are not in orbits the way that planets are in orbit around the sun, and we've talked about this in previous videos. They are in orbitals, which are really just probability distributions of where the electrons can be, but they're not that well defined. So you might have an orbital, and I'm just showing you in 2 dimensions. It would actually be in 3 dimensions, where maybe there's a high probability that the electrons, where I'm drawing it in kind of this more shaded in green, but there's some probability that the electrons are in this area right over here, and some probability that the electrons are in this area over here, and let's say even a lower probability that the electrons are over like this over here. And so you might say, well, okay, at a moment the electron's there, the outermost electron, let's say, is there. You might say, well, that's the radius. But in the next moment, there's some probability, it might be more likely that it ends up here, but there's some probability that it's going to be over there. And then the radius could be there. And so electrons, these orbitals, these diffuse probability distributions, they don't have a hard edge. So how can you say what the size of an atom actually is? And there's several techniques for thinking about this. One technique for thinking about this is saying, okay, if you have two of the same atom that are, or of the 2 atoms of the same element that are not connected to each other, that are not bonded to each other, that are not part of the same molecule, and you were able to determine somehow the closest that you could get to them to each other, so without them bonding, so you were kind of see what's the closest that they can kind of get to each other. So let's say that's one of them, and then this is the other one right over here. And if you could figure out that distance, that minimum distance, without some type of, really, I guess, a strong influence happening here, but just the minimum distance that you might see between these two, and then you could take half of that. So that's one notion, and that's actually called the van der Waals radius. Another way is, well, what about if you have 2 atoms, two atoms of the same element that are bonded to each other? They're bonded to each other through a covalent bond. So a covalent bond, we've seen this in the past. The most famous of covalent bonds is a covalent bond. You essentially have two atoms. So that's the nucleus of one, that's the nucleus of the other, and they're sharing electrons. So their electron clouds actually overlap with each other. So in a covalent bond, the electrons in that bond can spend some of their time on this atom and some of their time on this atom right over here. And so when you have a covalent bond like this, you can then find the distance between the 2 nuclei, and take half of that and call that the atomic radius. So these are all different ways of thinking about it. Now, with that out of the way, let's think about what the trends for atomic size or atomic radii would be in the periodic table. So the first thing to think about is, what do you think will be the trend for atomic radii as we move through a period? So let's say we're in the fourth period and we were to go from potassium to krypton. What do you think is going to be the trend here? And if you want to think about the extremes, well, how do you think potassium is going to compare to krypton in terms of atomic radius? I encourage you to pause this video and think about that on your own. Well, when you're in the fourth period, the outermost electrons are going to be in your fourth shell. Here you're filling out 4s1, 4s2, then you start backfilling into the 3d subshell, and then you start filling again in 4p1, 4, and so forth and so on. You start filling out the p subshell. So as you go from potassium to krypton, you're filling out that outermost fourth shell. Now what's going on there? Well, when you're at potassium, you have 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You have 19 protons and you have 19 electrons. Well, I'll just draw those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But you only have one electron in that outermost, in that fourth shell. And so let's just say that's that electron at a moment, just for visual. It doesn't necessarily have to be there, but just to visualize that. So that one electron right over there, you have 19, and you have 19 protons. So there's going to, you have some, I guess you could say, Coulomb force that is attracting it, that is keeping it there. But if you go to krypton, all of a sudden you have much more positive charge in the nucleus. So you have 1, 2, 3, 4, 5, 6, 7, 8. I don't have to do them all. You have 36. You have a positive charge of 36. Let me write that. You have plus 36. Here you had plus 19. And you have 36 electrons. You have 36 electrons. And I've lost track of them. But in your outermost shell, in your fourth, you're going to have the 2s, and then you're going to have the 6p. So you have 8 in your outermost shell. So that would be 1, 2, 3, 4, 5, 6, 7, 8. So one way to think about it, you have more positive charge in the center, and you have more negative charge on that outer shell. So that's going to bring that outer shell inward. It's going to have more, I guess you could imagine one way, more Coulomb attraction right over there. And because of that, that outermost shell is going to be drawn in. Krypton is going to be smaller, is going to have a smaller atomic radius than potassium. And so the trend as you go to the right is that you are getting, and the general trend I would say, is that you are getting smaller as you go to the right in a period. And that's the reason why the smallest atom of all the element with the smallest atom is not hydrogen, it's helium. Helium is actually smaller than hydrogen depending on what technique you use to measure it. And that's because if we take the simplest case, hydrogen, you have one proton in the nucleus, and then you have one electron in that 1s shell. And in helium, you have two protons in the nucleus, and I'm not drawing the neutrons, and obviously there's different isotopes, different numbers of neutrons, but you have 2 electrons now in your outermost shell, and so you have more, I guess you could say, you could have more Coulomb attraction here. This is plus 2, and then these two combined are negative 2. They're going to be drawn inward. So that's the trend as we go to the right, as we move from the left to the right of the periodic table, we're getting smaller. Now what do you think is going to happen as we go down the periodic table? As we go down the periodic table in a given group? Well, as we go down a group, each new element down the group, we're in a new period, we're adding a new shell. So you're adding more and more and more shells. Here you have just the first shell, now the second shell, and each shell is getting further and further and further away. So as you go down in the periodic table, you are getting larger. You're having a larger atomic radius depending on how you are measuring it. So what's the general trend? Well, if you're going larger as you go down, that means you're getting smaller as you go up. You get smaller as you go up. So what are going to be what's going to be the smallest ones? Well, we've already said helium is the smallest. And what are going to be some of the largest? What are going to be some of the largest atoms? What's going to be the atoms down here in the bottom left? So these are going to be large, these are going to be small. So large over here, small over here, and the general trend is you go from the bottom left to the top right, you are getting smaller. In the video on solubility, I draw little pictures of sodium and chloride ions when sodium chloride dissolves or dissociates into water. This is sodium and this is chloride. And my simple brain, when I looked at it, I said, okay, how should I draw these things? I said, well, they're in the same period. And sodium is a group 1 element. It's alkali. It's an alkali metal, while chlorine is a halogen. So chlorine is going to have a smaller atomic radius. And the logic there, just to review from the atomic table trends, is that they both of their valence electrons are in the third shell. Sodium only has 11 protons pulling in the center, has 11 in the center. And it has only 1 electron out there in its valence shell. So the attraction isn't as strong as the case of chloride, which has 17 protons in the center. And then, so it will, although it has more valence electrons, it has 7 of them. What is that? 1, 6, 7. These protons are going to have a stronger attraction on them. And so if you just look at the trend in the periodic table, you'd expect the sodium neutral atom to be bigger than the chloride neutral atom, because this guy has more protons pulling everything in. And that's how I drew the ions in that video. I said, oh, well, when I dissociate in water, I'll have a big sodium ion and a smaller chlorine ion, which is incorrect. Because think about, and this was pointed out to me by one of the viewers, and they're correct, and I should have realized this. What happens when you ionize these things? This guy will lose an electron, right? He gives the electron to this guy. So his electron configuration is actually going to look a lot more like neons. He now will have no electrons in that third shell, in the third energy state. So now he's going to have an atomic radius that's actually much more similar to neons here, right? Because he's going to have filled up the second shell. So actually the sodium ion, this is completely incorrect. The sodium ion is going to have an atomic radius not that different than neon. Actually, it'll be even a little smaller than neon because it has the same electron configuration, but it has 1 more proton. So the sodium ion is actually going to be smaller because it gets rid of the electron in that third shell. And the chlorine ion, cation, gained an electron. So it's completely completed its third shell. So here you have where the chlorine ion is going to be bigger. So in that solubility video, I should have actually switched the places between the sodium and the chlorine, at least in size-wise. And of course, I show how they dissociate in water, and this would be attracted to the oxygen end of the water, and you have the hydrogen ends and all that. But you can watch the solubility for that video for that. It doesn't change the real takeaway from the video, but I think this is a really interesting point that brings up that when you ionize these neutral atoms, it can significantly change, especially significantly change their relative atomic sizes. Anyway, hopefully you found that interesting.
In this video, we're going to look at atomic and ionic radii. And first, we'll start with the atomic radius. So if you think about an atom as a sphere, the idea of atomic radius is simple. You would just take this as a sphere here, and then a sphere, of course, would have a fixed and defined radius. And so that would be one way of thinking about it. The problem is that an atom doesn't really have a fixed, defined radius like the sphere example, because there's a nucleus, right? And then there's this electron cloud, or this probability of finding your electron. And so there's no real clear defined boundary there, and so it's difficult to have a fixed and defined radius. So what chemists do is they take 2 identical atoms, so let's say these are 2 atoms bonded together, the same element, and if you find their nuclei, so let's say that that's their nuclei here, and you measure the distance between those 2 nuclei, so this would be our distance d between our 2 nuclei. If you take half of that distance, right, that would be a good approximation of the atomic radius of one of those atoms. And so that's the idea behind the definition of atomic radius. Let's look at the trends for atomic radius, and first we'll start with group trends. And so here we have two elements found in group 1, so hydrogen and lithium. And let's go ahead and sketch out the atoms first. And so we start with hydrogen, which has atomic number of 1, which means that it has 1 proton in the nucleus. So here's our nucleus for hydrogen. Okay, so 1 proton. In a neutral atom, right, the number of protons equals the number of electrons, and so therefore there must be 1 electron. So we go ahead and sketch in our electron here, and we'll make things really simple and just show this this simple version of the atom, even though we know it doesn't really exactly look like this. And when we do lithium, right, atomic number of 3, so that means 3 protons in the nucleus of lithium. So this is representative of lithium's nucleus with 3 protons and 3 electrons. 2 of those electrons are in the inner shell. So let me go ahead and show 2 of lithium's electrons, right, in the inner shell. So that would be in the first energy level. And then we need to account for 1 more. So lithium's 3rd electron is in the second energy level, or the outer shell in this example. And so here we have our 2 atoms. And you can see as you go down a group, right, as you go down a group, you're going to get an increase in the atomic radius. And that's because as you go down a group, you're adding electrons in higher energy levels that are farther away, right? So in this case, we added this electron to a higher energy level, which is farther away from the nucleus, which means that the atoms, of course, would get larger and larger. So you're adding more stuff to it. So it's kind of a simple idea. Let's look at period trends next. So as you're going across a period this way, so as you're going this way, you're actually going to get a decrease in the atomic radius. And let's see if we can figure out why by once again drawing some simple pictures of our atoms. And so lithium, right, with atomic number of 3, so we've already talked about that, right? So there are 3 protons in the nucleus of lithium. So I'm going to go ahead and write that in here. So 3 positive charge for the nucleus of lithium. And then we have to account for the 3 electrons, right? So once again, 2 of those electrons were in an inner shell. So there we go. And then we had 1 electron in an outer shell. Okay, so the picture is something like this. Now let's think about what's going to happen to that outer electron as a result of where it is. So this outer electron, this one right here in magenta, right, would be pulled closer to the nucleus, right? The nucleus is positively charged, that electron is negatively charged, and so the positively charged nucleus is going to pull that electron in closer to it. At the same time, those negatively charged inner shell electrons are going to repel it, right? So let me go ahead and highlight these. These guys right here, right? These are our inner shell electrons, right? Like charges repel. And so you can think about this electron right here wanting to push this outer electron that way, and this electron, right, wanting to push this electron that way. And so the nucleus attracts the negative charge, and the inner shell electrons repel the outer electron. And then we call this shielding, because the inner shell electrons are shielding that magenta electron from the pull of the nucleus. So this is called electron shielding or electron screening. Now that's going to be important concepts. So now let's go ahead and draw the atom for beryllium. So atomic number 4, and so here's our nucleus for beryllium. With an atomic number of 4, that means there are 4 protons in the nucleus, so a charge of 4 plus in our nucleus, and we have 4 electrons to worry about this time. So I'll go ahead and put in the 2 electrons in my inner orbital, right, in our first energy level, and then we have 2 electrons in our outer orbital or our second energy level. And so again, this is just a rough approximation for an idea of what beryllium might look like. And so when we think about what's happening, right, we're moving from a charge of 3 plus with lithium to a charge of 4 plus with beryllium. And the more positive your charge is, right, the more it's going to attract those outer electrons. And when you think about the idea of electron screening, right, so once again, we have these electrons in green here shielding our outer shell electrons from the effect of that positively charged nucleus. Now you might think that outer shell electrons could shield too, right? So you might think that, oh, this electron right here in magenta, right, could shield the other electron in magenta. But the problem is they're both at pretty much the same distance from the nucleus. So outer shell electrons don't really shield each other. It's more of these inner shell electrons. And because you have the same number of inner shell electrons shielding as in the lithium example, right? So let me go ahead and highlight those again, right? So we have 2 inner shell electrons shielding in beryllium. We also had 2 inner shell electrons shielding in lithium. Because you have the same number of shielding, but you have a higher positive charge, right? A higher positive charge, those outer electrons are going to feel more of a pull from the nucleus, and they're going to be pulled in even tighter than you might imagine. So, or at least tighter than our previous example. So these electrons are pulled in even more, and because of that, you're going to get the beryllium atom as being smaller than the lithium atom. Hence the trend. Hence, as you go across a period, right, you're always going to increase in the number of protons, and that increased pull, right, is going to pull those outer electrons in closer, therefore decreasing the size of the atom. All right, let's look at ionic radius now. And ionic radius can be kind of complicated depending on what chemistry you are involved in. So this is going to be just a real simple version. If I took a neutral lithium atom again, so lithium, right? So we've drawn this several times. Let me go ahead and draw it once more. Right, so we have our lithium nucleus, which we have 3 electrons. So once again, we'll go ahead and sketch in our 3 electrons real fast. 2 electrons in the inner shell and 1 electron in the outer shell, like that. And let's say you were going to form a cation, right? So you're going to take away an electron from our neutral atom. All right, so we had, let me go ahead and draw this in here. We had 3 protons in the nucleus and 3 electrons. Those cancel each other out to be a neutral atom. And if we were to take away one of those electrons, right, so let's go ahead and show lithium losing an electron. All right, so if lithium loses an electron, it's going to lose that outer electron. So the nucleus still has a +3 charge, right, because it has 3 protons in it, and we still have our 2 inner shell electrons like that, but we took away that outer shell electron, right? So we took away this electron in magenta. So let me go ahead and label this. So we lost an electron. So that's this electron right here. And so you could just show it over here like that. And by doing so, right, now we'd have 3 positive charges in our nucleus and only 2 electrons. And so therefore our lithium gets a +1 charge, right? So it's Li+, it's a cation. And so we formed a cation which is smaller than the neutral atom itself. And that just makes kind of intuitive sense, right? If you take away this outer electron, right, now you have 3 positive charges in the nucleus and only 2 electrons here. So you're pulling those electrons in. You lost that outer electron. It's getting smaller. And so the cation is smaller than the neutral atom. And so we've seen that neutral atoms will shrink when you convert them to cations, so it kind of makes sense that if you take a neutral atom and add an electron, it's going to get larger. And so that's our next concept here. So if we took something like chlorine, right, so a neutral chlorine atom, and we added an electron to chlorine, right, so that would give it a negative charge, right, so we would get chlorine with a negative charge, or the chloride anion, I should say. And so in terms of sizes, right, let's go ahead and just draw a representative atom here. So if this is our chlorine, our neutral chlorine atom, and we add an electron to it, it actually gets a lot bigger, all right? So the anion is bigger than the neutral atom. And let's see if we can think about why here. So if we were to draw an electron configuration, or should write a noble gas electron configuration for the neutral chlorine, right? So you should already know how to do this. You would just write your noble gas in brackets, so neon, and then 3s2, 3p5, so seven electrons in the outer shell for the neutral chlorine atom. For the chloride anion, right, you would start off the same way. You would say neon in brackets, 3s2, and you would be adding an electron to it. So it wouldn't be 3p5, it'd be 3p6, like that. And so now we would have, so this would give us 8 electrons in our outer shell, and this would give us only 7 electrons in our outer shell. Now, the explanation for the larger size of the chloride anion in most textbooks is, you'll see people say that the addition of this extra electron here, right, so that means that those electrons are going to repel each other more. You have 8 of them instead of 7, and so because they repel each other more, it gets a little bit bigger. And that makes sense, but you'll see some people disagree with that explanation, and I haven't really seen a great alternative offered. And so however you want to think about it, generally the anion is larger than the neutral atom. But and in terms of the explanation for that, you could think about it as electrons repelling each other if you wanted to, despite the fact that people disagree with that. You could think about just more stuff as a really simple way of thinking about it. But again, in general for exams, think about the anion being larger. Ionization energy refers to the energy that's required to remove an electron from a neutral atom. So if we look down here, this A represents a neutral atom, meaning equal numbers of protons and electrons. And since the positively charged nucleus is going to attract those negatively charged electrons, it's going to take energy to pull an electron away from that attractive force of the nucleus. And so that's your ionization energy. If you take away an electron, you no longer have equal numbers of protons and electrons. You'd have one more proton than you do electrons. So you get a +1 charge here, so you form an ion. And so ionization energy is always going to be positive. So it always takes energy to pull an electron away. So a positive value for ionization energy. And our units are kilojoules per mole. And in this video, we're only going to be talking about the first ionization energy, so IE1, like that. Let's look at some actual ionization energies for elements in group 1. And so we can see here some elements in group 1. And so for hydrogen, right, it would take 1,312 kilojoules per mole of energy to pull an electron away from hydrogen. For lithium, it would take about 520 kilojoules per mole to take an electron away. And we can see as we go down here, the number decreases. So sodium would be 496, potassium would be 419. So there's a clear trend as we go down a group in the periodic table, right? There is a definite decrease in the ionization energy. So it must be easier to pull an electron away. So let's see if we can figure out the reason why, and we're going to study in detail here these two elements, so hydrogen and lithium. So let's go ahead and look at these diagrams here. We're going to fill them in for hydrogen and lithium. And so for our first diagram, we will put hydrogen. So hydrogen has atomic number of 1, so there's 1 proton in the nucleus, so +1 charge in the nucleus, and in a neutral atom, there's 1 electron. So I'll go ahead and draw on hydrogen's 1 electron right here, like that. The electron configuration would be 1s1, so that 1 electron is in an s orbital in the first energy level. Alright, so this negatively charged electron feels an attraction for this positively charged nucleus, and so to pull it away you must add energy. So if you add 1,312 kilojoules per mole of energy, you can pull that electron away, and if you do that, you'd be left with just a +1 charge in the nucleus and no electrons around it. And so you no longer have a neutral atom, you have an ion. You have H+, because you have a positive charge of 1 in the nucleus and 0 electrons, so H+. So that's the concept of ionization energy here. Let's look at lithium, right? So down here we'll draw lithium. Lithium has atomic number of 3, so 3 protons in the nucleus, and in a neutral atom, 3 electrons, right? So the electron configuration is 1s2, 2s1. So there are 2 electrons in the first energy level, and they're in an s orbital. So I'm going to go ahead and draw those in here. So these 2 electrons I just drew represent the 2 electrons in the first energy level. In the second energy level, there's 1 more electron. So I'm going to put that electron down here like that. So for lithium, if we were to take an electron away, the one that's most likely to leave would be this outermost electron here, the one in the 2s orbital. So if you apply 520 kilojoules per mole of energy, right, you can pull away that electron. And so if you did that, you'd be left with a +3 charge in the nucleus, right? And you would still have your electrons in the 1s orbital. So I'm going to go ahead and draw those in there. But you've taken away that outer electron, and so therefore you'd have a lithium cation here. You'd have Li+1 because you have 3 positive charges in the nucleus and only 2 electrons now. So 3 minus 2 gives you +1. The electron configuration for the lithium cation would therefore be 1s2 because we pulled away that outer electron in the 2s orbital.
So this is the picture for the ionization of hydrogen and lithium, and we're going to examine some of the factors that affect the ionization energy. And so first we'll talk about nuclear charge. So let me go ahead and write nuclear charge here. So the idea of nuclear charge is the more positive charges you have in your nucleus, the more of an attractive force the electron would feel, and so therefore the harder it would be to pull that electron away. So in general, you can think about increased nuclear charge, that would want to increase the ionization energy because again there's a greater attractive force for the electron. So let's look at these two situations, and let's think about hydrogen first. So hydrogen has a +1 charge in the nucleus, and this one electron here would be pulled to the nucleus by that positive charge. If we look at lithium, right, +3 in the nucleus, right, so that's a greater nuclear charge. So just thinking about nuclear charge alone, right, you would think, oh, well, this electron might be pulled in even more than with hydrogen because +3 is greater than +1. And so just thinking about nuclear charge for these two things, right, that would seem to indicate that lithium would have that lithium's outer electron would have a greater attractive force for the nucleus, and so therefore you might think it might take more energy to pull that electron away. So just thinking about nuclear charge, we might think an increase in the ionization energy. All right, next let's talk about electron shielding. So electron shielding, or you could also call it electron screening. So the idea of electron shielding is the inner shell electrons are going to shield the outer electrons from the positive charge of the nucleus. And let's look at lithium for an example of that. So we have these two inner shell electrons, right, are going to repel the outer shell electron. So this electron in blue is going to repel this electron in green, and this electron in blue is going to repel this electron in green. And so they're going to shield that outer electron in green from that +3 charge, because electrons repel other electrons, like charges repel other like charges. And so that's the idea of electron shielding or electron screening. And so thinking about just this factor, right, for lithium, these two inner shell electrons are going to shield that outer shell electron. There's going to be a force in the opposite direction, if you will. And so that means that it would be easier to take that outer electron away. So due to the repulsive force of those electrons. And so if you just think about electron shielding or electron screening by itself, right, it would be easier to take away lithium's outer electron due to the shielding effect, and so therefore you would need less energy, so a decrease in the ionization energy for just thinking about this factor. Now, nuclear charge and electron shielding go hand in hand, and one way to relate those would be to think about what's called the effective nuclear charge. So I'm going to go ahead and write the effective nuclear charge, so ZEF, is equal to the nuclear charge, which is Z, minus the effect of the shielding electrons. And so this is one way to think about it. This is a very simplistic way of doing the math here. So let's look at hydrogen first and calculate the effective nuclear charge that this electron experiences. Well, there's a +1 charge in the nucleus, right? So that's the nuclear charge, Z. And there are 0 shielding electrons, so 1 minus 0 is of course +1. So this outer electron experiences an effective nuclear charge of +1. For lithium, right, there are 3 protons in the nucleus, so Z would be +3. And there are 2 shielding electrons, these 2 inner shell electrons here, so it would be +3 minus 2. So the effective nuclear charge would be a +1. So if you think about it, the effective nuclear charge that hydrogen's electron feels is about the same as lithium's outer electron. So because they both have an effective nuclear charge of +1. So the fact that lithium has this electron shielding or electron screening, right, that kind of cancels out this effect of the nuclear charge. And so these two things kind of cancel out. Now, of course, this is a very simplistic way of calculating the effective nuclear charge. In reality, for lithium, if you do it the more complicated way, you actually get a value of approximately 1.3. So we can say that lithium's effective nuclear charge is close to +1, even though it's a little bit more accurate to say it's around 1.3. And so for our purposes, the electron shielding for lithium cancels out that increased nuclear charge. And so we have to look at the last factor to understand this trend. And the last factor is the distance of that outer electron from the nucleus. Right? So let's think about that. So for hydrogen, right, this electron is pretty close to the nucleus, and the closer it is, the more of an attractive force it has for the nucleus. So once again, in physics, Coulomb's law, it's distance dependent. The closer you are, the more of an attractive force you will feel. So that electron feels a very strong attractive force, so it's hard to pull that electron away. For lithium, right, this outer shell electron is on average, right, a further distance away from the nucleus, and so therefore it doesn't have as much of an attractive pull towards the nucleus. There's not as great of an attractive force, so it's easier to pull that outer electron away. If it's easier to pull that outer electron away, that of course would mean a decrease in the ionization energy. So because of distance, we can say that it's easier to pull that outer electron away from lithium because it's further away from the nucleus. And so thinking about all three factors at once, right, the nuclear charge and the electron shielding effect sort of cancel each other out. And so we can just think about the distance factor to explain the trend that we see in groups for ionization energy.